Welcome back to the latest lecture session. In the last session, we started talking about different variations of activated sludge process. In that context, we looked at or briefly discussed sequential batch reactor. This is something that's now being widely adopted in India, right? Sequential batch. So, in sequence, we have different batch reactors. What's a batch reactor? Now, a closed system that's continuously mixed or well stirred, let's say. But the key aspect is there is no flow coming in, no flow going out. So, it's a closed system. So, why do we say sequential batch? So, in the same tank which we are going to look at now, initially they will fill the tank with wastewater. So, they will keep filling it with wastewater. So, once the relevant level has been reached, they will stop the flow, right? And then what are they going to start? They are going to start mixing and providing oxygen. So, you are going to have aeration. So, during this aeration, the microbes are going to degrade the relevant waste and their substrate for their own cell synthesis and energy requirements. After this, they are going to stop the aeration, and now what do you have? You have flocks, these microbes that we promoted by maintaining the right conditions, and these flocks will settle down. So, in this case you have settle, you will promote settling, and afterwards, after some time, you will have all these or most of the flocks settle down with some filamentous microbial or microorganisms. So, you will have clear water at the top. This clear water you will remove, right? So, decanting, it is called decanting. So, each process more or less we can say is a batch reactor. So, sequential batch reactor, right? So, that is something to keep in mind. Again, better efficiency, and I think we talked about this earlier, let us not go back there. And then obviously lesser area requirements, and again looks like especially in India where we are not sure when the power is going to be available and not. SBR is a better process because you have greater flexibility, right? Again, we are going to look at the IIT Roorkee plant. Let me directly switch over there. So, a brief overview. So, here we have the sump where all the wastewater is going to be collected by gravity. It goes to the primary treatment here, but in this primary treatment we are not looking at sedimentation tanks or such to remove suspended solids. We are only looking at core screens and grit removal, right? But again, this is, I think they are calling it by a trade name. So, that is what we have. It is not the typical primary treatment. And after this primary treatment, the flow is coming out here, let us say. So, from sump, and obviously this is at the lowest level. And why is it at the lowest level? In IIT Roorkee, the sewerage network flows by gravity, as is the case in most other places by gravity. So, the end point will be pretty low, and then as we discussed, you will have pumping or headworks or such, and here we have a submerged pump that is lifting the water up to this particular treatment unit here. Here we have the core screens and grit removal, right? And from here you are going to have the water going to these sequential batch reactors. We have two sequential batch reactors, reactor 1, reactor 2. And here you see, some tanks out here. These are the bioselector tanks or bioselectors. Why or what is it that we are trying to do there? So, after this primary treatment, again in primary, let me not say primary, let me only call it preliminary treatment, you have wastewater that is high strength, relatively high strength anyway. And we know that we want flock forming microbes to be formed, right? But again, high F by M, right, is when these flock forming microbes thrive. But if I let that stay through the entire system, you are going to have pin flocks, you are going to have to achieve both kinds of filamentous, some filamentous and flock, right? And also you want to prevent the growth of nocardia type of microbes, right? So, we want to create the conditions that lead to the growth of the kind of microbes that we want. So, these are called the bioselector tanks. So, what do we have? these tanks with high strength wastewater. So you have some sludge or microbes that are put in, and they are aerated for some time, let's say 15 minutes, let's say, right? And so you have air, oxygen, so it's aeration, you have aeration and aerobic conditions for most of the time, and then you have a lot of food for the microbes, and you have some microbes because you are putting in microbes too. We'll look at that. So F by M is high in this particular bioselector tank. So the kind of microbes that thrive there are going to lead to rapid degradation, or the kinetics are going to be faster, and the kind of microbes that we want are typically going to thrive there, right? That's what happens in these bioselector tanks. You want the kind of microbes you want to prevail to grow, so that's why you are creating high F by M conditions in this tank. You can't create that over the entire tank because then your effluent quality will be degraded, right? So you are now having these bioselector tanks. After that, this water, right, which is already in contact with microbes, will be released into your sequential batch reactor, right? So let's go ahead and play this video. You have two tanks, sequential batch reactors, and then it goes to this disc filter, more or less a kind of mechanism to remove any further suspended solids, disc filter, and then you have a UV lamp based disinfection system, and then it goes to a particular underground tank out here, and these are the offices where you have the fully automated I believe the SCADA system, if I am not wrong, to control this process. These are not manually operated. The level of oxygen and such, which is key, right, is maintained, via or remotely, let's say, right. So you can see the relevant parameters and such. So the underground tank, I guess, why do we use that? Because this water is recycled for the maintenance of IIT Roorkee lawns and such, and the remaining water which can't be used for IIT Roorkee lawns is discharged into the Ganga Canal, right? Ganga Canal, which goes for, or which is the source of water for cities downstream of Roorkee. So that's one aspect, right? Okay. And then what happens out here? What else do we have? So as we mentioned, the sludge settles down. Until now, we haven't talked about it in detail, but after the sludge settles down, again, you can't throw it out onto the road. You have a lot of, when we say sludge, again, it's cells, microbial content cells, right? If I just leave them out there without oxygen or food, they are going to die, and again, septic conditions, decaying and such, right? So you don't want that. You want to be able to treat the sludge. But the issue with sludge is, even though it's well thickened and has settled down, you will still have considerable water content in it. So without removing this water content, if you try to degrade it, the volume and not just volume, again, because of the water that's there, both volume and the weight will be high. So transportation costs, treatment costs and so on will be high. So you want to dewater the sludge, or remove as much water as you can from these microbes, let's say. So here you are going to have sludge removed and brought out here, where you have the dewatering system here, right? And then we are going to have some stabilization or composting of the relevant sludge. That's a different aspect, but I guess that's what we see out here. Again, coming into the sump, right? Preliminary treatment and grit removal, and then SBR, and the sludge from the SBR goes to this dewatering system. So let me move on. Okay, now we have the video which we were able to take, right? So here we have the sump and the dewatering system, right? Let's just look at what we have. Okay, here you see the wastewater flowing in, right, at a lower head, obviously, or lower elevation. That's what we saw earlier. And from that particular sump, based on the, or using the submerged pumps, the water is pumped up to this unit where grit removal and removal of plastics and such takes place. Again, this is not the usual one that we see though, right? So let's see what else we have out here. So now we are looking at, after the preliminary treatment, core screens and some grit removal, what do we have? We saw that the water is being pumped up to the bioselector tanks, right? Bioselector, as in we want to have high F by M conditions such that the kind of flock forming microbes that we want to thrive will be predominant later or even now, right? So that's what we want to achieve here. So aeration is not going to be continuous here though for 15 minutes or such, high F by M ratio, let's say, right? So that's what we have. The water is flowing into this bioselectors here. That's what you see, right? And this is the sludge that's coming into these bioselector tanks. You see the sludge out here. Yes, and this is the water coming in from the left into the bioselector tank, and this is the sludge coming in. This is not the actual, I mean, the SBR is coming later, but this is what these are the bioselector tanks we have, so that the kind of microbes that we want thrive. This is the sludge coming in, right? That's how sludge with microbes looks, and this is the wastewater within that tank. So this is an SBR, an overview of the SBR tank, right? And the bioselector tanks are somewhere out here, let's see, okay, somewhere out here, which we can't see from this angle. From there the water comes in, and here we are seeing the aeration phase. Again, the whole cycle is 4 hours. Obviously we can't look at the whole 4 hours. So here I guess we have the filling, or okay, filling was done, and we have aeration. So you see the aeration bubbles coming in, right? And this is the line for providing air, and you see the air being pumped in, let's say. We'll look at the kind of diffusers that they are using, but the air is being continuously pumped in, aeration. So we are providing the oxygen, which is the electron acceptor, so that the microbes which are in the sludge that we added here, right? So that's why it's called return activated sludge, right? The microbes that are in the sludge that we added earlier or are adding will be able to use this oxygen and complete that redox process, let's say, right? So that's what we have out here. This is a SBR tank. Again, we have tank number 1 here, and tank number 2 is to our right hand side, which is not visible in this angle, let's say, right? So while aeration might be occurring here, decantation would probably be occurring in the other tank. So let's move ahead. So we have aeration, just a close-up view. So you can see the color, and again this is due to the MLSS, mixed liquor suspended solids, which has a lot of microbes in it, let's see, right? High microbial concentration. So just after they stop the aeration, you can see the kind of flocks that are being formed, right? So I guess just after we stop aeration or such, this is what you see. Okay, the shot here that we took was, here you see wastewater near a dead zone, right? You can see the color, and here you can see the MLSS or microbes and the wastewater on the left hand side, let's see, right? So you can see that. In a moment or so, we will be able to see the relevant flocks also. So decanter, which will come into play later once we are trying to remove this relevant supernatant, right? So this is when we stop the aeration, right after we stopped aeration, or they rather, and you see these flocks. Okay, this is a good angle. You can see the flocks, right? You can see these flocks. All these are flocks, and you can see already, let's say, 1 centimeter of clear water above. So these flocks are settling down by gravity now, right? So it takes some time, again 1 hour, 1.5 hours, or 45 minutes, depending on the cycle that they have optimized. Again, you can see the flocks that are being formed in this aeration tank or the SBR system, let's see, right? First fill, then aeration, which we looked at, and now settling down is taking place. See, you can see the flocks in a pretty decent manner, right? Okay, so this, I guess right now, this is the, earlier was the close-up shot, this is the long view when, you know, the water is settling down, not water, pardon me, the flocks or the sludge are settling down. Here settling is taking place, let's see, right? Let's move ahead. So settling, again from the top, it doesn't look like much, but obviously when we just stopped aeration and the flocks were at the surface, you could see the difference acutely, and over time the microbes are going to settle down, or the sludge is going to settle down. After we provided enough time for these microbes or the sludge to settle down, right? Again, type 1, maybe not type 1, type 2 settling probably initially, and then type 3 and 4. What are you going to have? You are going to have relatively clear water on the surface, and that water is being decanted, decantation. The water at the top is being removed, let's say, right? So that's what you have out here. This is decantation, right? So you can still see gentle or quiescent conditions elsewhere, and here you see the water being decanted. Again, as I mentioned, this is in one tank. In the other SBR tank that we have, you know, probably aeration is taking place or filling is going on. Decanter 1 and decanter 2, as I mentioned earlier. Again, a long view. So here you can see the 2 SBR units, one here where I guess decantation is taking place. On the left, as you can see aeration is taking place there, right? The two cycles keep going on in different tanks, let's say. So that's this is one good shot for us to understand that, you know, cycles are going on, but they are not the same, right? They go in different times, let's say, right? So here decantation and here aeration. Let's move on. So here I wanted to demonstrate how sludge settles, and also we did a minor trial to show what's going to happen if I add electrolyte, let's say, so that I can neutralize the charge and form or promote coagulation and thus flocculation. So, but first we are going to look at this particular beaker. So, this was collected just before aeration was stopped from the aeration tank. So, here you see water, and by the time we set up the shot, already you see that the sludge has started to settle down. Sludge is nothing but the microbes here that are degrading the relevant wastewater here, right. So, you can see the flocks here and relatively clear water at the top. This is real time now. Look at how it settles down, right. I'll just stop commenting for some time and we will look at it real time. Here, because the height of the settling basin, if I may call so, is only a few centimeters, you will have maybe initially type 2 and then type 3 compression settling and type 4 settling, 2, 3 and 4 visible at the same time, occurring simultaneously, I guess. But you can see within, I think, 30 seconds, you see that the sludge has settled a considerable, what do we say, distance here, right? Not distance, height here. Again, we did not add anything. So, when we stop aeration and just look at or have settling, this is what happens. All the sludge or the microbes, because they are now heavy, lesser surface area per unit mass, relatively heavier, what do? They form flocks and they settle down. Obviously, during this time, I don't want to provide air and mixing, right, or then they won't settle down. I want to provide quiescent conditions. So, that is what we saw. So, in this trial, I just, for the sake of an experiment or for demonstration, I asked the relevant engineer there to add a flocculant or an electrolyte there, so that you can see how with the addition of the flocculant or the electrolyte, the flock formation changes and how they differently settle. But again, you don't add flocculant typically to sludge, but we just looked at the trial because we see this or we come across flocculation, coagulation and flocculation in the sedimentation tank. Okay, I guess this is a different angle, but soon they will add the flocculant. Okay, so I guess this is from a different angle with better camera and such, but here you can see the sludge blanket, hopefully, right. Again, you could see the time, it's again just 30 seconds, which I moved up, and you can see the sludge blanket, again type 2, 3, 4, and maybe now it's at 4 or 3, I guess, right, zone settling, and now here they are adding the relevant electrolyte, let's say, or the polyelectrolyte or the coagulant, not flocculant, pardon me, coagulant, and you are mixing it. So, the charge is being neutralized, if any charge, if any, but again this need not be done, we are just doing it for the sake of demonstration, let's say. Charge is being neutralized, gentle mixing, right, and all this is real time, and then we stop the mixing. Okay, this level of mixing is not required, but fine. We stop the mixing. Already you see the change in flock size. The flocks are now much bigger, and obviously because they are bigger, you can see that the flocks settle down remarkably fast or have already settled down, let's say, right. So, you see that there is a considerable difference in the time required for water to be separated from the flocks, especially because the flocks are now bigger and most of the suspended particles too have been captured, let's say, right. So, that is something that you see, right. Let me now take this forward. So, after sequential batch reactor, or the last stage was decanting, you are going to pump the not pump the water out, decant the water gently, right. You do not want to disturb the settled sludge or such which is being pumped out. So what do we have? We still have some suspended solids, as you can see. See, even after the sludge has settled out, but again this is only 30 seconds. Typically we give 1 hour or so, and the height is obviously 2 to 3 meters. So you still have some suspended solids, but typically it will be much clearer after I let it stay for 1 hour. So what's going to happen? I want to remove these suspended solids further. So in this case they have a disc filter, right? They have a disc filter. So at that time it was under maintenance. So water comes in and you have these discs out here, right? Let me just switch to the video where we have the discs being shown. So here we have a disc filter in my hands, okay? So you see that this acts as a filter, let's see. Yes. So the suspended particles are going to be trapped in that particular relevant filter. So let's go back to where we were. Okay, disc filter. This is rotating in general, so the sediments are going to be trapped and clear water goes through. After that, obviously what do we have? We want to kill the microbes, if any, that are harmful to us, but in general the pathogen concentration is going to decrease because the pathogens can't thrive in the system that we had, or the kind of microbial community that we have in the SBR system, but still there will be some pathogens. So you want to what do we say, inactivate them by UV, or you can add chlorine, but chlorine will have its own issues. So I would strongly suggest against chlorinating treated wastewater for the formation of, due to the formation of carcinogenic disinfection byproducts, let's say. With UV you are going to damage the DNA or RNA of the cell and or the microbe or the pathogen and affect its ability to replicate. So you have this UV, I guess, let's see UV here. So it's a flow through system, water comes in and goes through. When it's not working, I guess the bypass, but you know you have the UV lamps, right? I think submerged system, and the water flows through it. So UV lamp submerged, and we also talked about the sludge, right? The sludge or the settled sludge, right? The microbes. What are we going to do with that? We need to also treat that. So first you want to remove much more water from it. So you have this dewatering equipment here, and then the polyelectrolyte is added to the settled sludge, not to the whole water. So we saw that polyelectrolyte, what do we say, addition there. Let's move on. So polyelectrolyte, right, is added so that the bigger flocks are formed, and then you have the sludge going in. This is sludge now, right, the settled sludge, and it's going through the dewatering equipment or machine. Let's see where or what else we have. Okay, this is the sludge that has to be dewatered. As you can see, it's not the typical wastewater, it's sludge, and you see that after electrolyte the kind of flocks are different, but still there is enough water. So it's coming in at the top, it's going in like this, as you can see. It's a filter press system, right, and you can see the water being removed, I guess. Okay, sequentially you see less and less water in the system, but let's look at the filter cake. Okay, here you can see the outlet. After dewatering, this is the sludge or the microbes here, right? You can now see the dewatered sludge that's coming out of the filtered press. So obviously now the volume, and also because I removed the water, the mass is going to be less, and it's relatively easy for me to treat or transport and then treat this, right? So typically anaerobic digestion, but because it's a small plant in IIT Roorkee, anaerobic digestion is not really required. So let me also look at the kind of, or show you the kind of diffuser that they are using here, right? So what do we see out here? We see this is the diffuser, right? Air comes in through this. It's not deep, it's not entirely, the air does not go through the entire system. I guess, the block is somewhere out here, and it passes through this diffusion membranes, let's see, or these membranes or diffusers, pardon me, right? And I think you can see the small holes somewhere here. If I hold it, you can see the holes, and through this the air will come out, let's see. Thus, why do we want to do that in the first case? Obviously because we want to have smaller air bubbles. We talked about actual oxygen transfer efficiency and so on and so forth. The whole point is to convert the oxygen in the air such that it changes phase from the gaseous phase to the aqueous phase. We want dissolved oxygen for the microbes. So obviously, lesser the size of the bubble, the greater the surface area, right? And then the greater the mass transfer of oxygen. So that's why we have such systems, let's see, right? So I guess that's hopefully visible now, right? Okay. So with that, I will end today's session. Again, it's sequential batch reactor. The kinetics are better because it will allow me to have a greater average rate of removal of the waste. And as we see, even with respect to different flows, I can vary the relevant levels even without an equalization tank. As you see in this case, we had no equalization tank. But again, because it's a gated community with 15,000 people or so, you might not really need it if you size your SBR well, right? And we looked at how sludge is formed, how sludge is not sludge, microbes are formed, and how the MLSS looks like, if I may say so. How the sludge is settling, it settled very well. That's something we looked at. And how the water is decanted, and how the sludge is also dewatered, right? So with that, I will end today's session. Thank you for your patience.